Okay, so here we are again. I apologize about the chalkboard setup, but I left a lot of my supplies back over at Edmond North, and I wanted to get these recorded so that people could gain access to them as quickly as possible. So we're using an old chalkboard here. Hopefully we'll have enough room for everything we want to do. I'm more worried about the final vector example, and we'll see what we get on that. Now in the last one, we dealt with a very simple vector addition. We had two vectors that were at right angles to one another, and we added them together to get a resultant vector. That was something that ended up describing how far away we were. We went from Edmond North to OSU. This time, we're going to do just a general example. Where did I set my chalk? This one will do. Okay. This one, we've got two vectors. First of which is A, and it has a total length of 5. My 5s always look horrible anyway, sorry. It is at 135 degrees with respect to the positive x-axis. So A equals 5 at 135 degrees. Okay. We're going to take a look at B. Our B vector, where did I point him? He looks like this. B has a total length of 6 at 30 degrees beneath the positive x-axis. So B equals 6 at negative 30 degrees. Because we're below the positive x-axis. Okay? So we have both of our vectors. I want to find some vector set C that is A plus B. Alright? Shouldn't be too bad. Now this is our general equation that we want to solve, but right now it's not very useful to us because this is adding vectors. We can't just plug the numbers in there because a vector isn't just a number. It isn't just a magnitude. It also has direction, so we've got to take that into account. What we can do is we can split this down into our components. C sub x plus equals A sub x, A sub x plus B sub x, and C sub y equals A sub y plus B sub y. So we split these out into components. That makes them at right angles to one another, so we can actually do our math on them, like Pythagorean theorem, or apply our sines and cosines. We can only do that if we have a right triangle. If I try and add A and B together, if I draw them together, you can see here, this is A, B would be back down like this, and so the triangle that I end up with, oh, I'm sorry, that's not how you add them. I should draw it correctly if I'm going to show them added. It's tail to tip. So this is A. B would come back down like this, not drawn to scale. Let's see, A is 5, so B would be a little bit longer, something like this. And our end result would be C, which would start at the very beginning, go to the very end, but none of these angles are right angles, which means we can't do anything like Pythagorean theorem or our trig functions. Those only work on right triangles. Okay? But by splitting this up into the components x and y, we're making right triangles because x and y are always 90 degrees off from one another. So if we do it this way, we can add things together because we're putting them into individual directions, things that we can keep track of which way our vector points. Okay, so we really want to get our a sub x and our b sub x, and our a sub y and our b sub y, because then we can find out our components of our result. So let's start over here with A. So it points up like this. It has a total length of 5. And if this is 135 degrees, then we could do 180 minus 135 and find out that this is 45 degrees. Okay, so we've got a triangle. We've got an x component that goes that way, and a y component that goes that way. We'll call the y component a sub y, and the x component a sub x. Okay, well this is a right triangle, so I can do some math on it the way that I'm used to. a sub x, I know this angle here, this is 45 degrees, and I want to find out this side. So, if I'm dealing with angles and sides, one of my best bets is to use a trig function. So I'm going to write out so, ka, toa. All right, well I know my hypotenuse, my h. I know the angle, so I can use either sine, cosine, or tangent. And let's start off looking for our x. That is our adjacent side, because it's the side that's right next to our angle. And so ka is what I'm looking for. So cosine of theta, which is 45 degrees, equals my adjacent, which is a sub x, over my hypotenuse, which is the total length of a, which is 5. In fact, I'm going to go ahead and change that to 45 degrees. Okay? So I can multiply both sides by 5, and I get a sub x by itself. So I have 5 times cosine 45 degrees equals the x component of my a. All right, cool. So when I evaluate that, I end up with, let's see, this one should come up to 3.54. But hang on just a second. This one's a little bit more difficult of a question. Let's remember which direction we're going in, because our angle is with respect to 135. Our x component is pointed off to the left. Well, that's in the negative x direction, so we need to actually put a negative in front of this. Okay? So let's take a look at our a sub y. We could use Pythagorean theorem, this guy squared and 5 squared. We'd take 5 squared minus this guy squared equals a sub y squared. But let's go ahead and get some more experience with our trig functions. So this time, I still know this angle. I still know my hypotenuse. This time we're going to look at the opposite side, so that's going to have me focus on sine. Sine of 45 degrees equals a sub y over 5. And just the same as before, I'm going to multiply both sides by 5. So sine 45 degrees times 5 equals, we should come up with the exact same thing because it's in fact an isosceles triangle, 3.54. All right, this time do we put a negative on there? Well, let's check. Our y component, our x component points off to the left, so that one's negative. And our y component points up. Okay, well, up is in the positive direction, so no, this guy's going to be a positive. All right, now we're going to find the components of our b vector. I'm going to draw him out here. And he was at 30 degrees below the x-axis. So I have an x component here and a y component here. So this is b, he's 6, and this is b sub x, and this is b sub y, because the x component is here, left and right, in our x direction, and our y component is up and down, which is our y direction. Okay. Well, so, by the same thing, we're going to find that if we go looking for our b sub x, this is our adjacent side. Look again at our SOHCAHTOA. So we're going to find that I can draw out cosine, this time of 30 degrees, because we're dealing with this triangle. Cosine of 30 degrees equals b sub x over our hypotenuse, which is 6 this time. Okay, well, I'll multiply both sides by 6. And I find that my b sub x equals, I'm going to put it down there because I'm running out of room. B sub x is 5.20. Okay. And then taking a look like we did before for our y component, we find that sine of 30 degrees equals b sub y over 6. We're going to multiply both sides by 6. Okay. And we find that our b sub y equals 3. Wait a second. Which way is our b sub y vector pointed? It's pointed down. That means that we need a negative here, because it's in the negative y direction. All right, now we're set. We have both of our a sub x, our a sub y, and our b sub x, and our b sub y. We can go back to our equations here. Well, I can find that my c sub x equals a sub x, which is negative 3.54, plus my b sub x, which is 5.20. Okay, so c sub x equals Where did I write that guy down? There he is. 1.66. And you'll notice it's positive because we had a bigger component over here, and so it got rid of the negative but got much shorter. Okay. C sub y equals our a sub y, which is right there, a positive 3.54, plus our b sub y, which is a negative 3. Okay, so my c sub y equals 0.54. Yep. All right, now I know my components of c. Well, all I need to do now is draw out c. So I'm going to come over here. I know that in my x direction, I have positive 1.66. And in my y direction, I have a positive, so up, 0.54. Okay? My resultant vector is right here, which is my c, and that's what I'm looking for. I need this angle here to describe it. And this is a right angle because we had an x component and a y component. So we can do Pythagorean theorem, just like we've done before. A squared plus b squared equals c squared. And if you evaluate that, you will find that c, not c squared, equals 1.75. Okay? And now I need to find this angle. Well, we're going to look back again over here at TOA to know that tangent of theta equals our opposite, 0.54, over our adjacent, 1.66. And if you evaluate this, you should find that it comes up to 18 degrees. At least that's what I found. Okay, so finishing up, I would describe that C, which is the sum of vector A and B, comes up to my total magnitude, 1.75, at my angle, 18 degrees, above the positive x-axis. And there we go.